Okay, welcome back. Let's continue. We had begun looking at polynomials, and yesterday we looked at how to do division, how to divide two polynomials. And today I want to look at how to factorize. Now, the concept of irreducible polynomials, we want to look at irreducible polynomials. Now, this concept is similar to factorization of the integers. It's just similar thing that I want to look at, but now in regard with the polynomials. So, the integers, if you're given a composite number like 86, or let me say 8, the composite 8 can be reduced. I'm trying to use the term that I'm going to be using, reducible and irreducible. Can be reduced to 2 times 2 times 2. A composite number 6 can be reduced to 2 times 3, where the 2 cannot be reduced further. The 3 here cannot be reduced further. So these 2 and 3 are, we shall now call them factors. These are the prime factors of 6. Now, it's the same concept you want to look at as regards to polynomials. We want to see whether, if given a polynomial, can we reduce it and write it as a product of its irreducible polynomials. So, for instance, this 600 has been written as a product of two irreducible integers. Now, so this 3 cannot reduce it further. This is a prime number, and even this 2 can reduce it further. A number like 7, this one is irreducible. You cannot reduce it. You cannot factorize it. You cannot factorize it. So polynomials, we have those we can factorize and those we cannot. So those we cannot, we say they are irreducible. They cannot be factorized. And those that we can reduce are called reducible. So we will then factorize that can be reduced. So that is the concept I want us to look at, irreducible polynomials, and where the polynomials can be reduced, in other words, can be factorized, we will try and factorize those polynomials. Now, just from this onset, also I want you to note as we progress that it may be impossible to reduce a polynomial in one field. It may be impossible to reduce it in one field, but it may be possible to reduce it in another field. So it depends which field are you working on. So the fields we can reduce some polynomials in, and we cannot reduce them in other polynomial, in other fields. So again, the field will be very important. Which field are we working on? And so we will see that as we progress with examples. So to clarify, I've said that supposing you have polynomials, supposing P is a polynomial, and supposing you have other polynomials that can be factorized out of this P, then P can be written as a product of those polynomials. If we have polynomials that can be factorized out of this P, then P can be written as a product of those polynomials. So this is a very important concept. If you're given a polynomial, you must know how to factorize it, and so on. And you must know which one cannot be factorized. So this is a very important concept to us. Now let's look at this example. This example is just to emphasize what I've said, that you may want, it may be possible to factorize in some fields and difficult in other fields. Let's consider this polynomial here. If somebody was to tell you to factorize it from the onset, and it tells you to factorize it in the field of integers, then you would find that it's not possible. You cannot factorize it in the field of integers. You cannot find two polynomials which, when you multiply them, you will get this. When you're considering the field of integers, it's not possible, because the reason is because you see, what is the discriminant? What is the discriminant? What's the value of that is? Now, the discriminant, what is when this formula we used to use it in high school, while we were getting the value of x for a quadratic equation. So the value of x was in high school, we used to get the value of x this way, b square. This is b square minus 4ac over 2c. Now this b square minus 4ac is what we call the discriminant. B square minus 4ac. So this is what it tells us if the value of x exists. That is, if the value of x exists, then what is under the square root should be a real number, should be a positive number or zero, should be a positive number or zero. But for this case, when you check what is under the square root, the value of b here is 0. So 0 square minus 4, a is 1, the coefficient of x square is 1. And then c, the number is 4. So you can see that under the square root, what we have there is negative 16. Negative 16, you cannot get the square root under which is a real number. The square root of negative 16 is a complex number. It's a complex. You cannot factorize this under when you're considering the field of integers. But that does not mean that it can be factorized. As I said at the beginning, what fails to be factorized in one field, it can always be factorized in a different field. So we only say that a polynomial is irreducible depending on the field you're working with. Because it could be reducible in the field A, but reducible in field B, and so on. That is a point I wanted to emphasize. For instance, when you consider this same polynomial in the field of integers mod 8, then you find that this polynomial can be factorized as x plus 2, x plus 6, and I'll be showing you how to do this in a short while. Because when you look at this, when you multiply this, you get x squared, and x times that will be 6x, and then 2 times that will be 2x, and then 2 times that will be 12. So what is this? This is x squared plus 8x plus 12. And I said we are considering mod 8. So when you consider mod 8, this becomes x squared. 8x becomes 0. And 12 becomes mod 8. 12 mod 8. If 8 were to go into 12, the remainder will be 4. So you can see that I've been able to factorize this in the field of integers mod 8. But I was able to factorize it in the field of integers. So that is what I meant. That's what I meant when I said that when we consider polynomial as being irreducible, it only depends on the field we are working on. It might refuse to be factorized in one field, but accept to be factorized in a different field. So that is what I want us to look at, and then we look at how do you then test if a polynomial is irreducible in a given field. How do you test? So that's what I want us to look at. There are several methods for testing if a polynomial is reducible, and I'll consider the first approach by use of roots. So use of roots, we want to check if it has roots in this field. What do you mean by roots? For instance, if you have x squared minus 4, this is a polynomial, is equals to 0. No, not is equals to 0. This is a polynomial. So what are the roots? What are the roots for this? The roots for this will be plus 2 or negative 2. What do I mean by root? The word root, sometimes the word 0. So we use them interchangeably. You can use the word root or 0 or even solution. So what I mean by root to this, that value which when you replace, get f of x, f of that value becomes 0. F of that value becomes 0. For instance, you look at this. When I put 2, where there is x, it will be 2 squared, then minus 4, and that will give me 0. If I put negative 2, I get the same thing. Negative 2 squared minus 4 again gives me 0. So that means 2 is a root or is a 0 or is a solution. And even negative 2 is a 0 or is a solution. So we use them interchangeably. So what we'll be doing, therefore, given a polynomial in a given field, we want to check if that polynomial has roots. If it has roots in that field, then we say it's reducible. If it has no roots, then we say it's irreducible in that field. Of course, not with certainty, not certainty. Sometimes it could be irreducible, but you have to apply more other techniques. One technique may tell you it's irreducible. When you apply another technique, so we'll then look for what is the best technique that will tell us that this is reducible and this one is irreducible. So that when you say this one is reducible, you say with the finality. Now, so root tests, I've said we just want to check if that polynomial has roots in that field. Now, this is my first example. Show that this polynomial is reducible in Z mod 6. In this field, the field is this is our field. So we want to check whether it's reducible there. Of course, if I was to tell you factorize it in the field Z, the integers, then you may not factorize this thing. You may not factorize. You may take a long time to do that. You may not get integers. You may not get integers to use to factorize that. But in Z6, one is you can factorize this. So what we want to try and see which of these elements of Z6 is a root. Which of them is a root? So we try 0. We put where there is x, put 0. So this will be 0 squared minus 3. So that gives us, this gives us 3. In fact, you can write it as 3 and negative 3, or just write it as 3 positive, because we are doing it mod 6. We are doing it mod 6. So no, negative 3 is the same as 3 mod 6. What about if we put 1? So that means this is not, 0 is not a root, because it has not given us 0. So 0 is not a root. What about 1? If you place 1 here, if 1 squared minus 3, which is negative 2. And of course, it's not 0. What about 2? Try 2. That would be 4 minus 3, and that is 1. And of course, that is not 0. What about 3? 3, that would be 9 minus 3. That is 6. And of course, we are doing this mod 6. So this is 0. So it means 3 is a root. 3 is a root. What about 4? If you put 4 there, that would be 16 minus 3. That would be 13. We are doing this mod 6, which comes to what? Is it supposed to be 1 or what? It is 1, eh? Did I multiply properly? I used 4. 4, that would be 16 minus 3. That is 13. This is 1. Is it 1? How come I wrote it as 5? It's not 5. If 6 were to go there twice, and the remainder is 1. Okay, but the thing is, this is not 0. What about 5? That would be 25 minus 3. That would be 22 mod 6. What does that become? 6 goes there 3 times because of 18, and you get 4. So again, this is not equal to 0. So we found one root. We found this. But this quadratic equation, it must have 2 roots. It must have 2 roots. So it means this root is repeated. It means it's repeated. That's what it means. It's repeated. We have it. It's repeating itself. Because this is a quadratic question. A quadratic question has 2 roots. It cannot have 1. But we find all the values that are supposed to be roots. All the values supposed to be roots are mod 6 are 5, and only 1 was a root, and it means it repeats itself. Good. So that means it can be factorized. So what is the factorization of this? It can be factorized from what I'm saying. Because what we found is that x, therefore, is 3. X is 3. So it means if x is 3, if I take this on the other side, it means x minus 3 can divide this polynomial. Can divide this polynomial. Because 3 is a root. 3 is a root. So if I take 3 the other side, it means this, what do we call this? This is a factor. X minus 3 is a factor. It's a factor of the polynomial. A factor. A factor, you understand what I mean? For instance, when I'm talking about 6, the factors are 2 and 3. So we've now found that x minus 3 is a factor. It means it can be multiplied by something else to give us the original polynomial. Let's see what that something else is using our yesterday's knowledge of division. Using yesterday's knowledge, let's see, x goes into x squared, x times, then that times that, you get x squared minus 3x. Let me just write this one properly. So when you subtract, you have 3x. Then you bring this one down, minus 3. So x goes there, plus 3. So 3 times that, this, you get 3x minus 9. And when you subtract this, you have 6. But we are doing it mod 6. We are doing it mod 6. So this is some. So we then found What we've then found, just a minute, my internet. We found that the factors of the original polynomial are x minus 3 and x plus 3. Those are the factors. So we've now factorized it. In fact, we factorize this polynomial. In fact, when you try and try to prove, if you multiply that, you get x squared. Multiply this, you get 3x. Multiply this, you have minus 3x. And multiply this, you have minus 9. We are doing this mod 6. Of course, this one gives us 0 here. You have x squared minus 9, but we are doing it mod 6. So when we just add 6 ones, you have x squared minus 3. If you add the 6 ones. So you can see that this polynomial we were able to factorize, but how did we do it? We were doing, because we are doing it mod 6, we tried to find out what are the factors, first of all, what are the roots? What are the roots of the polynomial? And we tried all the values, mod 6, and found that 3 was one of them. 3 was one of the factors. Now, so look what how I've written this. From my working, this is what I've got. But there's no problem if you're to write it this way. There will be no problem. They mean the same thing. These two mean the same thing. You've just reduced this mod 6. Because it's negative 3 mod 6. When you reduce this, you know this will give you 3. So again, this gives you the same result. That's why I said 3 was repeated. So, of course, this will be x squared. And x times that will be 3x. Then 3 times that will be 3x. Then 3 times 3 will be 9. And so when you do this will be x squared plus 3. And this is the same as the original, the one we were given. This is what we were given. What we were given was x squared minus 3, which we can also write as x squared plus 3, because this mod 6, this negative 3 mod 6 will be positive 3. So just the same thing. So long as you know you are dealing with mod 6, it becomes very easy for us. But now the method we are looking at is use of roots. So we're trying to find out what are the roots. Let me take another example just to emphasize that point. Show that this is irreducible. So it means we must show that there's no root. It has no root mod 6. That's what we want to show. So we try all the values mod 6. Want to see if there is a root. So we try 0, x to be 0, this will be 0, this will be 0, then that will be 2. So 0 plus 0 plus 2, that is 2. So this is not 0. What about 1? To be 1 square, which is 1 plus 2, and this is 4. So again, it's not 0. It's not 0, so it's not a root. 1 is not a root, 0 is not a root. Let's see 2. 2 square will be 4 plus 2 plus 2, and this is 8. No, this is 6. But the 6 is 0. Then plus 2, which is 2. 3, this will be 9 plus 3 plus 2. Of course, 9 is 3. Of course, 9 is 3. We are doing mod 6. And of course, this again is 0, then plus 2. If you want, you can just add 9 plus 3, which is 12, then plus 2, which is 14, and reduce that mod 6 and carry the same 2. What about 4? It will be 4 square plus 4 plus 2. But 4 square is the same as negative 2 times negative 2. Then plus 4, then plus. So this is 4 plus 4. 4 plus 4 mod 6 is 2. Then plus 2, that gives you 4. I'm reducing this way so that I don't use a calculator. But if you want, you just have done 16, then plus 4, that gives you 20, plus 2, that gives you 22, and then reduce mod 16, no, mod 6. 6 go there 3 times because of 18. Because of 18, then 18 from that 22 will come with 4 here, and 4 is not equal to 0. What about 5? 5 is the same as negative 1. So negative 1 square plus, you can even say plus negative 1, and then plus 2. Because x is 5, so 5 is negative 1. Mod 6. So this would be 1 minus 1 plus 2 is 2, and this is not equal to 0. So you can see we've tried all possible roots, and they have refused. They have not. None of them is a root. None of them is a root. We've tried all of them. None of them is a root. So it means this polynomial is irreducible in Z mod 6. In Z mod 6, it's irreducible. But that does not mean that we cannot reduce it in another field. We can reduce it in another field. But the thing is, we are at this point, we are considering Z6. So under Z6, it cannot be factorized. It cannot be factorized under Z6. Now, show that this is reducible in Z7. Again, we try the roots. We try the possible roots. These are the possible roots. So we want to find out if one of them is a root. They're just possible roots. So which of them is a root? That's what we want to see. So I try 0. Where x is, put 0, 0, 0. So I'm left with 30. Mod 7, 30 mod 7, that is 2. 30 mod 7. This is 2. Okay, now try 1. This will be 1 cubed minus 4 minus 11 plus 30. And so what is this? This would be negative 3. Yes, this 2 gives you negative 3. Negative 3 minus 11, that is negative 13. Negative 13 plus 30. That gives you 17. That gives you 17 mod 7. So if 7 were to go into 17, go there 2 times because of, am I really right here? Let me just again redo it because I'm saying 17 minus 14 is supposed to give me 3 and I wrote 2. Let me see whether what I wrote is correct or what I'm saying now. Okay, let me again do it. And you can assist me if I'm not doing it properly so that we move together. 1 cubed will be 1. Then 1 square will be 1 times 4 will be negative 4. This is negative 4. And then 11 times 1 will be that. And then plus 30. So then I said that this 2 gives me negative 3. Negative 3 minus 11 will be negative 14. And that is why I went wrong here. I wrote 13 instead of 14. So then this gives me 16. 16. So 7 goes into 16 2 times. The remainder is 2. So what I wrote was correct. What I wrote was correct. What about 2? 2 cubed will be 8. And then 2 square here will be 4. 4 times 4 will be 16. And then 11 times 2 will be 22. Then plus 30. We are doing it mod 7. So in fact, if you want, you can begin reducing mod 7. Or even these two gives you 8. And these 2 give you negative 8. So that is 0. If you use your calculator, it will get 0 there. So that means 2, therefore 2 is a root. 2 is a root. When you do the same, you find that 3 is not a root. And 4 will be a root. 4 is a root. When you do it, you find that 4 is a root. 5 is another root. And 6 is not a root. This is a cubic equation. Cubic, we require 3 roots. And we have already the 3 roots. These are the 3 roots. So it means x is equals to 3. We have, those are the solutions to this. And then we have x is equals to 4. Then you have x is equals to 5. So when you bring 3 to the other side, you would have x minus 3. Then you have x minus 4. Then you'll have x minus 5. We have factorized this polynomial. We have factorized it. So this is how you factorize. First of all, you find the roots and then you just multiply the factors. Because these are the factors. When you multiply those factors, you get the polynomial.
Is it 3 or 2? X minus 2.
Oh, yes. Thank you. It was a 2 here. It was a 2. So x was a 2. So that is what we have. Thank you. So that's what we have for that. So we factorize this polynomial. Now, this is not the only way you can want to write this. This is not the only way. You may want to change those negatives to positives. You want to change those negatives to positives by just adding 7. And it's the same fact. So when you add 7 to this, you have x plus 5. When you add 7 to this, you have x plus 3. And when you add 7 to this, you have x plus 2. And again, this is, when you multiply this, you must get the original polynomial. And when you multiply this one also, you must get the original polynomial. The only difference is that the original polynomial is not mod 7. It's not mod 7. That's where the only difference will come in. The original polynomial is not mod 7 because this number is not mod 7. This number is not mod 7, and even this one is not mod 7. If you were to do it mod 7, then the original polynomial is supposed to be x cubed plus 3x squared, and then plus 3x, and then plus 2. Because 7 goes here 4 times because of 28, and the remainder is 2. And here you add the 7, negative 11 plus 7, that is negative 4. Then plus another 7, that is 3. So this, if you are to convert the original equation to mod 7, this is how it will look like. But there's no need of doing that. So when you multiply this, you must get either this or this, and the two are the same equations. Let's just try one. Let's just try the last one here. Let's try this last one. This will be x squared, then plus 3x. Then 5x. Then 15. So what is this? This is same as x squared plus 8x plus 15. And if you want, you can reduce this mod 7, but let's leave it. We can reduce later. Now, let's multiply the remaining factor, x plus 2. So x plus 2 multiplied by what we have, x squared plus 8x plus 15. So this will be x cubed, and then 8x squared, and then 15x. Now do with it using 2, it will be 2x squared, then plus 16x, that is 16x, then plus 30. Okay, now like terms, and so we have x cubed. Just a minute. Okay, write it here. Yeah, we have x cubed. X squared, we have 8 plus 2, which is 10. Then x, you have 15 and 16, which is 31. Then we have 30. You may now want to reduce them mod 7. When you reduce them for mod 7, this goes to 3. And this one minus 28 again goes to 3. And this goes to 2. Then you have this equation here. So whatever factorization, because you're dealing with the mod 8 and you understand mod 7, and you understand how modulus arithmetic goes, it becomes very easy and very interesting. Now we've been able to factorize this polynomial in Z7. But you may find that in another field, you cannot factorize it in another field. But we were able to factorize this in mod, the field of integers mod 7. Yes, that is how we do it. And so our intention, therefore, is to try and see how do we write a code that will assist us to do this factorization. And those are the steps we are looking at. And if so, the steps, it means you want your code to try all the possible scenarios. Mod 7, for instance, you want your code to try mod 0, try 1, try 2, try 4, try 3, and so on. And it has to find out if there is a fact, if there is a root. And so it must give you the roots if they exist. Once it gives you the roots, then you know that the polynomial is factorizable, is reducible, and you can now factorize. You can now factorize the polynomial. Now, this point, I'm just emphasizing that a polynomial may be reducible. It may be irreducible in one field, but reducible in another field. So when it's irreducible in one field and reduced, we don't say that it cannot be reduced in another field. We know that it can be reduced in another field. It's only that we at that point, be considering some other field. For instance, this, we were able to factorize this. We were able to factorize it mod 8. Was it mod 8 or mod 6? We did this earlier. I think it was mod 6 or mod 8, whichever. We did factorize this. But of course, you can also factorize it under complex numbers. If the field is that of complex numbers, then it can factorize it this way. You know complex numbers? These are numbers which are written in the form a plus ib, where I is imaginary. I is imaginary and has the property that the square root of it is I. As a property that I square, you can say I square, I times I is -1. I times I is negative. You know the square root of -1 is I. That's the square root of -1. But we also know the square root of 1. The square root of 1 is just 1. But when you talk of the square root of -1, that becomes I. So that the square root of something like 4 is the same as, no, -4. The square root of -4 is the same as the square root of 4 times the square root of -1, which is plus or minus 2i. Is plus or minus 2i. So that is how, so it means this can be factorized this way. So that if you are to expand, x times x will be x squared. Then x times 2i will be 2i. Then -2i times x will be -2i. That's what I meant. This was supposed to be x times 2i would be 2ix. Then minus this 2i times x will be -2ix. Then this -2i times that positive 2i will be -4, but I times I will be -1. I times I times I, this I times that I will be -1. But this -2 times that 2 will be -4. So this 2 gives us 0 because they are the same. We are left with the x squared plus 4. We are left with x squared plus 4. So you can see what I am emphasizing here is that while we cannot factorize this under the real numbers, we can factorize it in another field, for instance, as the complex numbers or Z8 or Z, whichever, another field. It can be factorized in any other field, but it may not be factorized in other fields, but it could be factorized in other different fields. That is the point. Now, so that is the method, first method we've looked at. The first method we've looked at to find out if a polynomial is factorizable. We considered the roots of that polynomial. But the other method I want us to look at is what we call rational roots. Rational roots. And at this point, again, as I did last time, I want to define what a rational number is. A rational number is one which can be written in the form P out of Q, where Q is not equal to 0, and the GCD of these two numbers is 1. The GCD is 1. That means their only common factor is 1. Examples of rational numbers, as I did last time. A number like a half is a rational number. A number like 2 out of 3 is a rational number. A number like 7 out of 9. You see, their only common factor is 1. A number like 7 is rational because it can be written as 7 out of 1. A number like -20 is rational because it can be written as -20 out of 1. A number like 1 million is rational. So all the whole numbers we know are rational numbers. All the fractions that we know, where the only common factor is 1, are also rational numbers. So we now know what rational numbers are. So when we talk of the rational root test, is that we get given a polynomial and we want to find out which rational numbers could be roots. Which rational numbers could be roots? So it's related to the one we've just done above, only that we have a few skills that we then apply. We have a few skills that we then use. So supposing this is the polynomial, how do you apply the rational root test? Supposing this is the polynomial. So we say that this polynomial has a rational root P out of Q if, okay, where the only common factors here are 1. So in this method, what we want to do, therefore, we want to come up with all possible rational roots that exist for this polynomial. We want to come up with all possible. When I use the word all possible, I mean the ones we suspect could be roots. After we come up with all those, we then want to find out which of these could be now the exact root, which of them could be the root. So we come up with the roots we suspect, the numbers we suspect could be roots to the polynomial. The numbers we suspect, these are rational numbers. The rational numbers we suspect could be roots, we come up with them. After coming up with them, we now go one by one, verifying to see which of them then is a root. Now look at the P and Q, what properties P and Q should fulfill for them to be suspected to be roots. For P and Q to be suspected to be, for this to be suspected to be a root, for this number, of course, this is just one fraction. For this fraction to be suspected to be a root, the numerator should be a number that divides the constant term. Should be a number that divides the constant term. The numerator should be divisors of the constant term. What about the denominator? The denominator must be divisors of the leading coefficient. The leading coefficient. This is the leading coefficient. So we want to come up with this type of roots. Possible roots. Possible. So this possible, the numerator should be a divisor of the constant term, and the denominator should be a divisor of the term. After we come up with all those possibilities, and then we now go one by one, verifying to see which one is now the root. So what I've been explaining is just what I've written here, applying the rational root test. I've already explained what we are going to do. I said we're going to list the divisors of the constant term, then the divisors of the leading term, we list them. And then after that, we combine and see, we come up with the rational numbers, and then come and check which of the rational numbers we'll have formed then are roots. Which one are roots? So let me take an example here. An example of how to use the rational root test. I'm given this polynomial and I'm asked to see whether I can factorize it or whether it's not factorizable. That is, using the correct terms of polynomials, I want to check if this polynomial is reducible or irreducible in rational numbers. This stands for rational. This stands for rational numbers, the rational field, the rational field. So I want to check if it's factorizable or not. Now, I said we want to form rational numbers. We want to form rational numbers P out of Q, where P should be the divisors of the constant term, and Q should be the divisors of the leading term. So the divisors, numbers that can divide this constant term, one of them is +1 and -1. So that's how I said plus or -1. Then the other number that can divide 8 is +2 or -2. Another number that can divide 8 is +4 or -4. Another number that can divide 8 is +8 or -8. So we found the possible values of P. The possible values of P. What about numbers that can divide 3, +1 and -1, +3 and -3? Now let's now form fractions, possible roots, our potential roots. Our potential roots, if I divide 1 in all this, if I divide 1, this is my Q. If I pick this to be Q, then 1 into 1, I would have 1. 1 is a possible root. 1 into 2, I will have 2. 1 into 3, into 4, I will, okay, let me say, I'm considering +1. So if I consider +1, because this one has positive and -1. So, okay, that will make it so many, there'll be so many possibilities. So let me just take +1 and divide it into plus or minus 1. I'll have plus or minus 1, I'll have plus or minus 2. +1 divided by that, I'll have plus or minus 4, and then plus or minus 8. Even -1 will give me the same thing. If I take -1 and divide into all this, I'll still get the same thing, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. What about 3? Divide 3 into all those, you'll have plus or minus a third. I'll have plus or minus 2 out of 3. I'll have plus or minus 4 out of 3. I'll have plus or minus 8 out of 3. How many possibilities are these? 1, 2, 3, 4, 5. These are 16 possible roots. 16 possible roots. This, because this is +1, then -1. Those are 2 possibilities. +2 and -2, those are another 2. +4 or -4. So those are the possible roots. So this, the roots of this cannot come outside this. It must be one of these. You cannot get it from outside. It must be one of these. So we want to try all of this and see which ones are there for the roots. Which ones are there? Oh, sorry for that. I was using my phone and it went off. I thought I was charging, even because Jaga on. Okay, so we were trying to see which rational numbers are then the roots. So just try all of them. Where there is x, for instance, I may now want to take 3, and there is that negative a third, and then raised to 3, then 2, negative a third, raised to 2, then plus 12, negative a third, then minus 8. So when I did that, this is what I got. When you just do that, and then next you have 3, a third. I'm now trying a third. I tried a negative a third, and now I'm trying a third. So a third raised to 3, then 2, a third raised to 2, and then 12, a third, then negative 8. And when I did that, I got this. Then I tried 2 thirds. I now came to this option, tried 2 thirds, and it gave me 0. So I did not want to proceed, check all the rest, because these are 16 of them. You may not want to check all of them. Once you get 1, and yesterday we had learned the knowledge of division. Using that 1, you now can divide, get a quadratic equation, which you can again factorize. So what this means, we've just done and found that 2 thirds is one of the roots. So that means x can be written as that. In other words, x minus 2 thirds is a factor. So this is then what I want to divide into that polynomial to find out the quadratic equation that I can now factorize again to get the other roots. Instead of trying all these roots, I may now, once you get one root, proceed and factorize. That's what I've done here. I've said that the polynomial that I've been given f of x can now be written as x minus that this factor that we've just found times another factor times another polynomial g of x. Now, to get rid of this fraction, it's easier to multiply by this 3 here, that I have 3x minus 2, and then multiply by 3 this left side, that I just get rid of the fraction. I'm not saying that it's not good to work with the fractions. I'm just saying it would be hard working with the fractions, so make it easier by just multiplying by this 3 here, and then multiply it to the left side. So when you multiply by the left side, I now want to divide this here so that I can get g of x. I want to divide this here, 3 times that. So our original polynomial is here. When you multiply it by 3, you get 9x cubed, then get negative 6x squared, then get 36, then get 24. And then this other polynomial that I want to divide, I put it outside. And then just do the same division as yesterday until you get the remainder. So when you do that, I've already done that. You can try that at your own time. I divide this just as we were doing yesterday. You'll find that 3x minus 2 goes into this polynomial this number of times, and the remainder will be 0. So which means this polynomial is factorizable. This 9x cubed minus 6x squared plus 36x minus 24 is now factorizable as 3x minus 2 multiplied by 3x squared plus 12. So you can see it can be factorized to that. So what we now want is to factorize this, if it's possible. We want to factorize it so that we factorize the polynomial that we were given completely. because that is our mission, to factorize it completely. That it's written as a product of factors that cannot be factorized further. So this is what I've explaining. I've been explaining that it can be written this way. But you can see what is inside here can be factorized. 3 is a common term. So that is why I put 3 outside, and 3 goes here, x squared, and this is 4. So then I've factorized it this way. What about this? Is it factorizable further? And I've said it cannot be factored. So that means the maximum we can come is this. But this is, okay, so just let me go back. Let's explain. Let me press this. Recall that this was 2 out of 3, and this was x. Then we multiply by 3 here and multiply on the left side. So that left side is this, the 3 is here, and there's this 3 here, so they can cancel out. So when they cancel out, we are left with this. So this is the factorization of the original polynomial. This is the factorization of the original polynomial. Now, so maybe I can show you one example, then we go to the code. Just one example. How do you come up with P and Q? Just one example of how to come up with P and Q. We want to factorize this. So we want to come up with the possible roots in the form of P out of Q, where P are numbers which divide 6, and Q are numbers which divide 6, the leading polynomial, the leading term. So numbers which can divide this constant term are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And those which can divide this again are the same, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So what are the potential roots? Just divide 1 into each of these. You'll get 1, plus or minus 1, you get plus or minus 2, get plus or minus 3, get plus or minus 6. Then divide 2 into each of these. Get plus or minus a half. 2 into this, you get plus or minus 1, which you already have. Then plus or minus 3 out of 2. Then this into that will be plus or minus 3, which you already have. What about 6 into all of those? Divide 6 into all of those. Now plus or minus 6. And then 6 into this, you'll have plus or minus a third. Then 6 into this, you have plus or minus a half, which you already have, and so on. What about 3? I had skipped 3. 3 into all of those, plus or minus a third, which you already have. Then 3 into 2 will be plus or minus 2 out of 3, and so on. So these are the potential roots. The potential roots. So we want now to check which of them are the exact roots, because these are just potential roots. None of them, we cannot get roots outside this. Any root to this equation must be one of the ones you mentioned. It must be one of the ones you mentioned. You cannot get it from outside. Even if you try, you cannot get it from outside. It must be one of these. If it's not here, then there is no root. If it's not here. So I tried -6, it was not a root. No, -6 was not a root. I tried -3 was not a root. I tried 6 out of 1 was not a root. A third was not a root. But when I tried -2 out of 3, it was a root. -2 out of 3 was a root. So it means, therefore, x is equal to -2 out of 3. But you can bring this on this other side and get a factor. So you're now getting the difference between a factor and a root. So when I bring this on the other side, I get there's a factor 2 out of that. So this is one of the, if you have to factorize this polynomial, this would be one of the factors. If you have to factorize that polynomial, that is one of the factors. So now, for you to get the other factors, you only need to divide this polynomial into the original polynomial. You divide this factor into the original polynomial. So that's what I wanted to do here. That is what I'm doing here. I'm just saying that the original polynomial can be written as this factor times another polynomial. Now I want to get rid of this fraction. I multiply here by 3, and then I multiply here by 3, and that's what I get. That's what I get. So now this is what is here, and what is inside here is the original polynomial times 3, because the original polynomial is here. This is 6, multiplied by 3, you get 18. This is negative 17, multiplied by 3, you get negative 52, and so on. So when you divide this inside here, this is what you get. That's the polynomial you come up with. And so want to see whether that can, so you try and factorize that again. You see, to factorize that, you may want to use the knowledge we already have of getting two numbers whose product is that, and maybe the sum, the same way we're doing it in high school. Or if it's not possible, again, you use the knowledge of roots that we've learned, that we're still learning. Now, so this is what we did. We multiplied this by 3, and then we found it was giving this, and this is what we just obtained. But what we just obtained from this division can still be factored because 3 is common, so 3 can be put outside. 3 can be put outside. So when you put 3 outside, this 3 will then cancel with this other 3. And then you have the original polynomial, therefore, written this way. So this one, again, you may want to use the same method to factorize. You may want, again, you have this polynomial, you want to come up with P out of Q, where P are divisors of 3, which are this, and Q are divisors of 2, which are this. Then come up with this polynomial, these roots, possible roots, by just dividing 1 into all of those, and then 2 into all of those. Now, after you come up with these roots, as we've done before, find out which of them is a root. When I did, I found a half negative was a root. Then again, the same reasoning follows. So you'll follow later. Then on division, this is what I come up with. And our question was, it was Z what? We are doing it Z mod Z7. Just come back and check. On not mod for Z. We are doing it the rational numbers. Just a minute. Okay, so after you've gotten the roots, then what you come and just come and factorize. You come up with, you'll want to check this factorization whether it's proper. And you want to come and check later. Now this one I'll not do it, you just go through it, the same reasoning. The same reasoning. This one I tried and I found that there was no root. None of them will factorize. Now, this method of rational roots, now its implementation in Rust is here. It will do for you the roots, the beginning the roots, and you can see it's using that push. So after dividing by I, then it pushes if I is a root. If I is a root, so if I divides that polynomial. So of course it began the same way we began. The same way we began by identifying the possible roots. It began by identifying the possible roots. So that's what it's doing. That's what it's doing. So when it finds something is a root, it pushes it inside this vector. It finds it's a root, it pushes there, and then it collects all those. Of course, there are various functions here, and they're working together just to do that. They're working together, so you look at it later, and then maybe if we get time, we'll explain how it works. I can show you how I can just run it, then we end our class like that after I just run it. Just a minute, let me enlarge it first of all. And then I can now share it. Okay, so this is the program. This is the program. That's the same program I've been, you look at it later. Of course, it will be in my notes, so you can try and write it in your Rust programs, then try to implement it. This is my main, and this is the polynomial I want to factorize. This is the polynomial I want to factorize, so I've just entered it here. You can see this is the last term, the term without a constant term, then 11x, then negative 6x squared, then x cubed. So I want to know what are the roots. What are the roots? So let me just, first of all, just a minute, let me get the terminal. Okay. Cargo run. So I wanted to give me the roots of that polynomial. Once you get the roots, you can always factorize. You know, it just, so it has told us, for instance, for this polynomial here, the roots are this. So x is 1, or x is 2, or x is 3. That means this can be factorized. Using these roots, it means it can be factorized as x minus 1, x minus 1 times x minus 2 times x minus 3. So this is what this solution is telling us, that it can be factorized this way. So that is how you try later and try and see if you can write this and try to customize it so that it can do other functions. Okay, that is where I want to stop for today. Thank you.